Now, a critical component to understand is how far the spread of the data is. Data variance is critical to any analysis. Now, consider we have two data sets, and we talked about a box plot in the last module. We're going to use that again here. These two box plots demonstrate two different data sets. But let's assume one is one class and the other is another class. The middle line is almost identical, meaning their medians, or maybe it's their averages, are the same. But the spread of the grades is a little bit different. The difference is clear, and the analyst can easily make inferences about the data sets, because the second one has a lot of variation and the other one didn't quite have that much variation. Well, which do you prefer? Well, for dealing with sales, you might not want a lot of variation. The large variation might be a little bit more chaotic to deal with or represent more volatility. Let's look at how we get there. So the first thing is we need to compute like the minimum and the maximum, right? And those are pretty simple functions to understand. The min function will give us the lowest value or the minimum value in a column or a group of data, and the max will give us the highest value. So we have our minimum. In this case, again, using that same grades data set, minimum is 64 and the maximum is 96. The range of the data set is really going to be the maximum minus the minimum. So we're just going to obtain that by doing the 96 minus 64, which is 32. Now, what if the data has negative numbers? Well, if the data is a negative number, nothing special needs to be done. So here's an example where we have our minimum and maximum. So the minimum is negative 10 and the maximum is 34. If we just do that same subtraction, 34 minus a negative 10, it will show us the range is 44. And that's correct, because it's going to be 34 on the positive side, and then it's going to be 10 to the negative side. So we add that up and we get 44. So the range will never be negative. That's not going to happen. The variance is going to be the measure that we use to measure the spread. It's going to be the value that's going to tell us about the spread around the mean. And it is really a great measure of how far or near data is to a center point. It is the most fundamental metric or statistic in statistics. It is the thing that really is the most critical concept in terms of understanding, because all of the techniques we do will focus on this variance. Assume we have a data set here, 1, 10, 50, 75, etc., all the way to 1,000. And another data set, 1, 2, 2, 7, 8, all the way to 22. It's clear to see that the first set has a very wide range or dispersion, while the dispersion in the second set is much narrow. This is very similar to the box plots we just spoke about. To calculate the variance, first we have to measure how far each observation is from the mean. We're going to use our sample mean here as the center. So we know how to compute that average. We take each observation and subtract it from its mean. Now the problem is, since the mean represents the middle point, the numerator would be negative for items to the left below the mean, and positive numbers to the right above the mean. Now when we say the numerator, it's going to be that formula down below. That xi minus x bar is what we're going to use. But if we do this, we're getting a distance that could be negative, and that's going to be a problem, because distances can't be negative. So again, consider that we have an example where the sample mean is 10, but we're looking at an observation of 8. You do 8 minus 10, you're going to get negative 2. That's not really right. The distance is really 2. So since distances cannot be negative, it is solved by squaring the difference. So what we're going to do is we're going to square each of those numbers. Squaring the difference removes the negative numbers and also increases the magnitude for items that are further away. So think about if you have 9 minus 10, that's negative 1, and you square it, you're going to end up with 1. But if you had 1 minus the 10 and you have a 9 and you square it, that's going to be 81. So we're actually increasing the magnitude as items are further away, and that's going to give us this real concept of the variance. If those numbers are all added up, shown by this sigma, and divided by the items, the number of items that we have, the result is what we would call the average squared distance, and that is what the variance is. It's each individual observation minus the sample mean. We square them to get rid of the negative and enhance the items that are further away. We're adding them all up and then dividing by n. Again, when we did our adding up all the values and divided by n, that was our average. So this is basically nothing more than the average squared distance, and that is the variance. The population variance is the same formula that we had. The only difference is we're subtracting it from a population mean here and taking each one of those and dividing by n. So for example, the population mean for a human body's temperature is 98.6. Therefore, mu would also be 98.6. Also note that since the population variance is represented with the lowercase Greek letter sigma, sigma squared, that's what our variance is. It's going to be that sigma squared. The sample variance is a bit different. First, we're going to change the sigma squared to an s. So it's going to be s squared. Now, you're going to ask, why is it squared? I don't want to worry too much about that because we're going to take the square root to get something a little bit different in a minute. But the mu here is now replaced by an x bar. And the other thing that we're changing is instead of dividing by n, we're dividing by n minus 1. If we used n, the average is closer to the sample and not the population. By subtracting 1 from the denominator, it increases the average dispersion a bit. In other words, we're not dividing by the full amount, we're dividing by 1 less than the full number, so our average is not going to be quite right. It's a form of correction, and it's known as Bessel's correction. Excel automatically handles this for you when we calculate the variance. You won't have to do this. But it's a question that some people ask about why n minus 1, and it has to do with this concept of if you took n, it's getting you really much closer to the sample's average as opposed to a population. So we kind of penalize it. We do this correction by taking an n minus 1 instead. Now, as we said before, why was it the sigma squared? And it's because we're really going to take the square root of that, and we're going to get a standard deviation. The standard deviation is nothing more than the square root of the variance. There are 2 standard deviations here, one for the population denoted as sigma, and one for the sample denoted as s. But they're both obtained by taking the square root of their respective population and sample variances. And this is what we're going to focus on a lot. Did it have to be the sigma squared or not? No, it could have been any other symbol they chose, but by doing this, they've streamlined it to make this a little bit more clear. Now, understanding the standard deviation and why it's important is very simple if we use a graph. The power of calculating the standard deviation is that it can give you a better measure of the dispersion in the form of kind of like a percentage or some index value. Each unit of the standard deviation represents an area around the mean. So this yellow center line here is the mean. And the blue region is basically -1 to +1 standard deviations. If the data is normally distributed or looks like a bell curve, we will be able to apply the 68, 95, 99, 7 rule. That means that 68% of the data will fall within 1 or -1 standard deviation, 95% of the data will fall between plus or minus 2 standard deviations, and 99.7% of the data will fall between plus or minus 3 standard deviations. When calculating the variance and standard deviation in Excel, we just need to know whether we're looking for a population or a sample. So we have some data here to the right. I've consolidated them into 2 columns. This is really one data set, but they're all consolidated. So it's just 1 column of data, but I had to represent it as 2 for the presentation. The functions var.s and var.p will calculate the sample and population variance. And the functions stdevs and stdev.p will calculate the sample and population standard deviations. For these modules, we'll use the sample functions pretty much exclusively. Using the data set on the right, if we did var.s, we would get 130.4733. And if we did the standard deviation.s for that same data, we would get 11.4224. Now, just to prove that they're the same, if we took the square root of 130.4733, you would end up with 11.4224, which is the same as the standard deviation of the sample. In older version of Excel, var.s and standard deviation.s are var and stdev respectively. So you're going to see this backward or compatibility functions in Excel. You can just ignore those and just use the var.s and standard deviation.s. We have another concept called a coefficient of variation, and it's another measure of variation by examining the relationship of the standard deviation to the mean, and it's represented as a percentage. We take the standard deviation, divide it by the mean, and multiply it by 100. This is often used as a measure of variability of investments or as a measure of risk.